Welcome to the Sleepy Scientist. It is very good to have you here. Before we settle in, where in the world are you watching from tonight? Maybe you're tucked away in bed, listening in a quiet room where the lights are low. Maybe you're on a late train, half watching the window turn into a dark mirror. Maybe you are on the sofa with a blanket, a drink, and the sincere intention to stay awake for the whole video, which is always admirable, even when history suggests otherwise. Wherever you are, hopefully you're comfortable, safe, and ready to let your thoughts slow down a little. If these calm scientific journeys help you relax, a like and subscribe is always appreciated, and it helps this sleepy little channel keep drifting along. And to everyone who has already subscribed, thank you, truly. Your support gives these quiet explorations a place to keep growing. Now, tonight's subject is slightly risky because it is about the system that helps you feel, move, breathe, blink, swallow, dream, react, remember, balance, digest, and occasionally wonder why you walked into a room and immediately forgot the mission. A mystery known to science, and also to anyone who has ever gone upstairs for one thing and returned with a sock. So the aim is to keep things calm, even while exploring the network inside you that is never completely off duty. Even while you rest, your nervous system is quietly adjusting your heartbeat, shifting your breathing, sorting signals, filtering sensations, and keeping the body running with the calm competence of a night shift worker who never gets thanked properly. So let's begin, shall we? How does your nervous system quietly run your body? At this very moment, without needing to think about it, the body is carrying on a quiet conversation with itself. Signals are travelling from skin, muscles, organs, blood vessels, eyes, ears, and joints, moving through living tissue with a speed and precision that would be impressive even if it were happening in a machine. But this is not a machine. It is warm, breathing, slightly squishy biology, which makes the whole thing rather more astonishing. The nervous system is the body's fast communication and control network. It links the brain and spinal cord with the nerves that spread through the rest of the body, reaching into the skin, muscles, glands, sensory organs, blood vessels, and internal organs. It helps you feel the pressure of a blanket, adjust your posture, blink when something comes too close, notice a sound in the room, swallow without much ceremony, and keep breathing while your attention wanders somewhere else entirely. It is not only the system that lets you think and move, it is also the system that keeps the body quietly organised beneath thought. That is one of the most important ideas to settle into early on. The nervous system is often imagined as the place where thinking happens, as though the brain were a little command centre sitting in the skull, issuing instructions with great authority. And yes, thought is part of the story. Movement is part of the story. But the nervous system is far more intimate than that. It regulates breathing, heartbeat, digestion, balance, posture, temperature responses, pain, attention, sleep transitions, and emotional body states. It shapes whether the body feels calm or alert, heavy or restless, safe or tense. It helps decide which sensations rise into awareness and which are politely ignored, like a faint shirt label that the brain has decided does not deserve a full committee meeting. This is why the nervous system is not simply about the mind. It is about the entire living body. When the heart speeds up before a difficult conversation, when the stomach tightens during worry, when the shoulders relax after a deep breath, when the eyelids grow heavy at night, the nervous system is involved. It does not act alone, because the body is full of overlapping chemical, hormonal, immune, and mechanical systems. But the nervous system is one of the fastest ways the body coordinates itself. It is the great messenger, the regulator, the watcher, the responder, and sometimes the overenthusiastic smoke alarm. The most basic anatomical division is between the central nervous system and the peripheral nervous system. The central nervous system is made of the brain and spinal cord. These are the major processing centres, protected by the skull and the bones of the spine, wrapped in protective membranes, and surrounded by fluid that helps cushion and support them. The brain receives, interprets, compares, predicts, and coordinates. The spinal cord carries information between the brain and the body, but it is not just a passive cable. It can handle many fast responses locally, including reflexes that happen before conscious thought has fully arrived on the scene. The peripheral nervous system includes the nerves outside the brain and spinal cord. These nerves reach into the face, arms, hands, chest, abdomen, pelvis, legs, feet, skin, muscles, organs, and glands. They bring sensory information inward and carry motor and regulatory signals outward. They are the long travelling lines of communication between the central nervous system and the rest of the body. Without the peripheral nerves, the brain would be rather like a brilliant lighthouse with no windows, glowing impressively, but unable to receive much news from the coastline. Within this larger arrangement, there are several functional systems working together. The sensory system gathers information. It detects light, sound, smell, taste, touch, pressure, temperature, pain, body position, muscle stretch, and internal signals from organs. The motor system controls movement, from deliberate actions like reaching for a cup to subtle adjustments that keep the body balanced and upright. The autonomic nervous system regulates internal functions such as heart rate, blood vessel diameter, sweating, digestion, pupil size, and many glandular responses. The enteric nervous system, embedded in the wall of the digestive tract, helps coordinate the movement and function of the gut. It is sometimes called the second brain, although it is not quietly composing poetry down there. It is doing something more practical, which is usually what the gut prefers. These divisions are useful, but the real nervous system is deeply interconnected. Sensation affects movement. Movement changes sensation. Autonomic state changes attention. Emotion changes breathing. Breathing can influence heart rhythm. The gut sends information back to the brain. Immune signals can alter mood, energy, pain, and sleepiness. The body is not a set of separate apartments with locked doors. It is a living conversation, and the nervous system helps keep the conversation moving quickly enough for survival. The modern understanding of this system was not obvious at first. For a long time, scientists debated what nervous tissue actually was. Under early microscopes, the brain and nerves did not give up their secrets easily. They looked dense, tangled, and almost impossibly delicate. Then, in the late 19th century, the Italian scientist Camillo Golgi developed a staining method that made individual nerve cells visible in extraordinary detail. The Golgi staining method used a silver-based technique that coloured only a small fraction of cells, but those few cells stood out with their branching shapes revealed against the surrounding tissue. It was a little like walking into a dark forest and suddenly seeing one tree lit by moonlight, roots, branches, and all. Golgi himself believed that the nervous system formed a continuous network, a single connected web of tissue. But Santiago Ramón y Cajal, a Spanish neuroscientist and gifted observer, studied Golgi-stained tissue and came to a different conclusion. Cajal argued that the nervous system was made of separate cells. These cells communicated with one another, but they were not one continuous fused structure. This became known as the neuron doctrine, one of the foundation stones of modern neuroscience. Golgi and Cajal shared the Nobel Prize in Physiology or Medicine in 1906, even though their interpretations were famously opposed. It is one of science's more elegant, awkward dinners. Two researchers honoured together for work that helped reveal the same world, while disagreeing about what that world meant. Cajal's view eventually became the basis of the modern picture. The nervous system is built from neurons, supported by glial cells, arranged into circuits and networks. Neurons receive information, process it, and pass signals onward. They do this through electrical changes along their membranes and chemical communication at synapses. That cellular structure matters because it explains how the nervous system can be both unified and flexible. It is not a single unbroken wire. It is a vast community of cells linked by patterns of communication. The nervous system also has to be selective. If every signal in the body reached awareness at full strength, ordinary life would become impossible. The pressure of clothing, the tiny shifts in posture, the movement of the stomach, the rhythm of breathing, the sound of distant traffic, the feeling of the tongue resting in the mouth, all of it would crowd into attention at once. The nervous system constantly filters. It raises some signals, lowers others, and decides what matters according to context. A faint sound at midday may be ignored. The same sound at night may suddenly feel important, especially if the house has just made one of those mysterious wooden clicks that apparently all houses say for bedtime. Speed is equally important. Some signals must travel quickly because delay can be dangerous. Touching something hot requires a fast withdrawal. Losing balance requires rapid muscular correction. A sudden threat needs changes in attention, breathing, heart rate, and blood flow. Other processes unfold more slowly, such as learning, recovery, sleep regulation, and long-term adaptation. The nervous system operates across many timescales at once, from split-second reflexes to memories that can shape behavior for years. This speed and complexity come at a cost. The brain makes up only a small part of the body's mass, roughly about 1/50th in an average adult, yet it uses about 1/5 of the body's resting energy. That energy supports ion gradients, synaptic signaling, cellular maintenance, blood flow regulation, and the constant work of prediction and control. Even quiet thought is not free. Even rest is biologically busy. The brain may look still from the outside, but inside it is expensive tissue doing expensive work. And yet most of this work feels effortless. That may be the nervous system's greatest trick. It quietly keeps the body balanced, responsive, and alive, while consciousness receives only a narrow slice of the whole performance. You do not need to command the heart to beat, remind the pupils to adjust, calculate the angle of every joint, or supervise each breath through the night. The nervous system does not switch on only when something dramatic happens. It is always shaping the conditions beneath experience. So the nervous system is not a simple command chain. It is not a single control room. It is a layered living network of cells, signals, pathways, reflexes, predictions, and feedback loops. It listens to the world outside the body and the world within it. It turns pressure into touch, light into vision, vibration into sound, chemical change into sensation, and internal need into action. Quietly, continuously, and often without thanks, it runs the body beneath every moment. The nervous system is built from living cells, and its most famous cell is the neuron. A neuron is often described as a nerve cell, but it is more than a tiny biological wire. It is a specialized signaling cell shaped to receive information, make small decisions, and pass messages onward. Its form is part of its function. A neuron has dendrites, which branch outward like delicate trees and receive incoming signals from other cells. It has a cell body, which contains the nucleus and much of the machinery that keeps the cell alive. It has an axon, a long projection that can carry a signal away from the cell body. At the far end are axon terminals, where the neuron can pass information to another neuron, a muscle cell or a gland. The meeting place between cells is called a synapse. This is where one cell influences the next. Sometimes the communication is electrical, but most synapses in the human nervous system use chemical messengers. A signal travelling down an axon reaches the axon terminals, and this can trigger the release of neurotransmitters into the tiny gap between cells. Those neurotransmitters then bind to receptors on the next cell, changing its activity. It sounds small because it is small, but the effect is enormous. Every touch, thought, reflex, blink, swallowed sip of tea, and sudden decision not to say something foolish depends on these microscopic conversations. It is tempting to imagine neurons as simple wires carrying messages in straight lines, but that image is too neat. Neurons are living cells. They grow, adapt, change their connections, alter their sensitivity, and respond to the chemistry around them. Some neurons carry sensory information from the body toward the central nervous system. Some send motor signals outward to muscles. Others sit inside the brain and spinal cord, linking signals into networks that can compare, filter, amplify, silence, and reshape information. A neuron is not just a cable. It is a tiny participant in a vast living network. And neurons do not work alone. For many years, glial cells were treated almost like packing material, as though they were simply the quiet stuffing between the important parts. That view is now badly outdated. Glial cells are essential partners in nervous system function. Astrocytes help support neurons, regulate the chemical environment around synapses, influence blood flow, and help maintain the blood-brain barrier. Oligodendrocytes form myelin around axons in the central nervous system. Schwann cells form myelin around axons in the peripheral nervous system. Microglia act as immune-like cells of the central nervous system, constantly surveying their environment. Ependymal cells line the fluid-filled spaces of the brain and spinal cord and help with the movement and regulation of cerebrospinal fluid. Myelin is one of the nervous system's most elegant pieces of biological engineering. It is a fatty insulating layer wrapped around many axons. Instead of allowing an electrical impulse to crawl continuously along the whole length of an axon, myelin helps the signal move much faster. The gaps between myelinated sections are called the nodes of Ranvier. At these nodes, the electrical signal is regenerated so the impulse appears to leap from gap to gap. This process is called saltatory conduction, from a word meaning to leap. The signal is not actually becoming a tiny gymnast, but the image is not entirely unhelpful. Myelin allows long-distance communication to happen quickly enough for real life, where a delayed reflex or a sluggish step could be a genuine problem. The distinction between oligodendrocytes and Schwann cells matters because the nervous system is organized into different regions. In the brain and spinal cord, oligodendrocytes can wrap myelin around parts of several axons. In the nerves outside the brain and spinal cord, Schwann cells usually wrap around one segment of one axon. These support cells help make rapid signaling possible, and when myelin is damaged, nerve communication can become slower, disrupted, or unreliable. That is one reason myelin is not just insulation. It is part of the nervous system's timing system. The brain also needs a carefully protected chemical environment. This is where the blood-brain barrier becomes important. The blood-brain barrier is not a solid wall, but a selective boundary between the bloodstream and the brain's delicate tissue. It is formed mainly by endothelial cells lining the brain's blood vessels, with tight junctions between them that limit what can pass through. Astrocyte end feet press closely around these blood vessels and help regulate the barrier and the surrounding environment. This barrier allows the brain to receive oxygen and nutrients while limiting many toxins, pathogens, and sudden chemical changes. It is selective rather than sealed, which is useful because a brain completely cut off from supplies would be less a protected organ and more an ambitious disaster. Microglia add another layer of quiet maintenance. These cells patrol the central nervous system, responding to injury, infection, and inflammation. During development, microglia also help shape nervous system circuits by removing unnecessary synapses, a process called synaptic pruning. This pruning is part of how the young brain refines itself. Too many connections can be inefficient, and the nervous system must learn not only what to build, but what to trim back. There is something quietly garden-like about it. Growth matters, but so does careful removal. So beneath every sensation and movement, there is cooperation. Neurons carry and process signals. Astrocytes support and regulate. Oligodendrocytes and Schwann cells speed communication with myelin. Microglia watch, respond, and help remodel. Ependymal cells help maintain the fluid environment of the central nervous system. endothelial cells and astrocyte end feet help guard the brain's chemical surroundings. No single cell type runs the show alone. Every reflex, every change in posture, every touch on the skin, every breath adjusted in the background, and every quiet internal shift depends on these specialized cells working together. The nervous system feels seamless from the inside because its cellular work is hidden from awareness. But under that smooth experience is a busy living society of cells, carrying signals, protecting tissue, shaping connections, and keeping the body in conversation with itself. The electricity of the nervous system is not quite the same as the electricity in a plug socket, a battery, or a thundercloud. The body is not simply wired like a machine, with little sparks racing around inside it. Living electricity is gentler, smaller, and more chemical. It comes from charged particles called ions moving across the thin membranes of cells. In neurons, these ions shift in carefully controlled ways, creating tiny electrical changes that can carry information from one part of the body to another. A neuron has a membrane around it, and that membrane separates the inside of the cell from the fluid outside. On both sides of this membrane are ions, including sodium ions, potassium ions, chloride ions, and negatively charged proteins. These charged particles are not evenly spread. There is usually more sodium outside the neuron, more potassium inside it, and large negatively charged proteins trapped inside the cell. The membrane is also selectively permeable, which means some ions can cross more easily than others. This uneven distribution creates a voltage difference across the membrane. When a neuron is not actively sending a signal, it has what is called a resting membrane potential. In many neurons, this resting state is roughly around -70 millivolts, meaning the inside of the cell is more negative than the outside. That number sounds tiny because it is tiny, but in the microscopic world of a cell it matters enormously. The neuron is not asleep in this resting state. It is prepared. It is held in a delicate electrical readiness, like a quiet room where everyone is pretending not to wait for the doorbell. One of the key systems that helps maintain this readiness is the sodium-potassium pump. This protein sits in the cell membrane and uses energy from adenosine triphosphate, the cell's main energy-carrying molecule. The pump moves sodium ions out of the neuron and potassium ions into it, helping preserve the ion gradients that make nerve signaling possible. Without these gradients, neurons would lose the electrical difference that allows them to respond quickly. The sodium-potassium pump is therefore not an optional extra. It is one of the small, tireless workers, keeping the nervous system ready to speak. The modern understanding of these electrical signals owes a great deal to Alan Hodgkin and Andrew Huxley. In the 20th century, they studied the squid giant axon, a nerve fibre unusually large compared with most human axons. Its size made it easier to place tiny electrodes inside and measure changes in voltage. From this work, Hodgkin and Huxley developed a detailed explanation of how action potentials are generated. Their research became one of the foundations of modern neuroscience, helped by the fact that squid, quite unexpectedly, had donated a very convenient piece of biology to science. An action potential is the rapid electrical signal that travels along a neuron's axon. It begins when enough incoming stimulation brings the neuron to a threshold. Once that threshold is reached, voltage-gated sodium channels open. Sodium ions rush into the cell, and the inside of the neuron becomes less negative. This phase is called depolarization. For a brief moment, the electrical state of the membrane changes sharply, creating a travelling wave along the axon. Almost immediately, the sodium channels begin to close, and voltage-gated potassium channels open. Potassium ions move out of the cell, helping the membrane return toward its resting state. This phase is called repolarization. In some neurons, the membrane briefly becomes even more negative than its resting level before settling back again. The whole event is extremely fast, and yet it is carefully organized. The action potential is not a vague pulse. It is a precise sequence of channel openings, ion movements, and membrane changes. The shape and direction of the impulse depend on these voltage-gated channels. As one section of the axon depolarizes, it helps trigger the next section, and then the next. The signal travels forward because the region behind it enters a refractory period. During this short interval, that part of the membrane cannot immediately fire another full action potential. Some sodium channels are temporarily inactive, and the neuron needs a moment to reset. This refractory period is important because it stops the signal from bouncing backward and echoing uselessly along the axon, which would be biologically impressive but deeply unhelpful. In myelinated axons, the process becomes even faster. The electrical signal is regenerated at gaps in the myelin called the nodes of Ranvier, allowing the impulse to move efficiently along the nerve fiber. The underlying principle is still the movement of ions across membranes, but myelin helps make the timing sharper and the transmission quicker. The nervous system depends not only on whether signals arrive, but on when they arrive. All of this hidden electrical activity is constantly tied to ordinary life. When a fingertip feels the edge of a mug, sensory neurons are changing their electrical state. When a foot lifts during walking, motor neurons are sending signals to muscle. When pain warns the body to pull away, action potentials are carrying urgent information. When breathing continues quietly during rest, networks of neurons are using electrical changes to maintain rhythm. Beneath every calm moment, charged particles are moving, channels are opening and closing, pumps are working, and the body's soft electricity is keeping the conversation alive. Neurons can send electrical signals along their own membranes, but the nervous system becomes truly powerful when one cell communicates with another. Most neurons do not simply touch end to end, like bare wires joined together. Instead, they influence one another across tiny meeting places called synapses. A synapse is not just a gap. It is a specialized communication site where one cell can change the activity of the next. Some synapses are electrical, allowing signals to pass directly between cells through small channels. These can be extremely fast, which is useful in places where timing matters very precisely. But many of the most familiar and flexible signals in the nervous system are chemical. In a chemical synapse, the sending cell is called the presynaptic neuron. At the end of its axon are axon terminals, which contain tiny packages called synaptic vesicles. These vesicles are filled with chemical messengers known as neurotransmitters. When an electrical impulse reaches the axon terminal, it can trigger those vesicles to release neurotransmitters into a narrow space called the synaptic cleft. On the other side is the postsynaptic neuron, or sometimes a muscle cell or gland cell. The surface of that next cell contains receptors, shaped to respond to particular chemical messengers. When a neurotransmitter binds to a receptor, it can make the next cell more likely to send a signal, less likely to send a signal, or change its behavior in slower, subtler ways. This is one of the reasons the nervous system is not merely electrical. It is electrochemical. Electricity carries a signal along a neuron, and chemistry often carries the message between neurons. It is a little like a very fast relay, except instead of passing a baton, the runners briefly throw tiny molecular notes across a microscopic gap, and somehow the whole body keeps functioning. Biology does like to make simple ideas unnecessarily beautiful. The nervous system uses many neurotransmitters. Glutamate is the major excitatory neurotransmitter in the brain, meaning it often makes the next neuron more likely to become active. Gamma-aminobutyric acid is the major inhibitory neurotransmitter in the brain, meaning it often makes the next neuron less likely to fire. Acetylcholine is important at the neuromuscular junction, where nerves communicate with skeletal muscles, and it also plays major roles in attention, learning, and the autonomic nervous system. Dopamine is involved in movement, motivation, learning, reward prediction, and several brain circuits. Serotonin helps regulate mood, sleep, appetite, pain processing, and many other functions. Norepinephrine is involved in alertness, attention, arousal, and stress responses. Histamine helps regulate wakefulness. Glycine is an important inhibitory neurotransmitter, especially in the spinal cord and brainstem. Endorphins are natural opioid peptides involved in pain modulation and the body's response to stress or exertion. It is important, though, not to turn these chemicals into cartoon labels. Dopamine does not simply mean pleasure. Serotonin does not simply mean happiness. Norepinephrine does not simply mean panic. These substances act in different brain regions, through different receptor types, at different times, and in different patterns. A neurotransmitter is not a single emotion in liquid form. It is more like a word whose meaning changes depending on the sentence, the speaker, the listener, and the situation. The nervous system is annoyingly subtle that way, as though it missed the memo requesting easier explanations. Excitatory and inhibitory signaling are especially important because the nervous system depends on balance. Excitation helps signals move forward, strengthens activity, and allows information to spread through circuits. Inhibition restrains activity, sharpens timing, filters noise, and prevents networks from becoming chaotic. Without enough excitation, signals may fade. Without enough inhibition, signals may become uncontrolled. The brain is not trying to be as active as possible. It is trying to be appropriately active, which is a much harder and more elegant task. The discovery that nerves communicate chemically was helped by the Austrian scientist Otto Lowy. In the early 20th century, Lowy studied the vagus nerve and the heart. In a famous experiment involving frog hearts, he showed that stimulating the vagus nerve released a chemical substance that could slow the heartbeat. That substance was later identified as acetylcholine. His work helped establish that nerves could send messages not only through electricity, but through chemicals released into fluid. It was a quiet revolution in understanding carried out with a heart, a nerve, and a surprisingly persuasive bit of biological soup. Once neurotransmitters are released, their effects must be controlled. Some are taken back into the presynaptic neuron through reuptake. Some are broken down by enzymes in the synaptic cleft. Some drift away. The postsynaptic cell can also change how sensitive it is by adjusting the number or type of receptors on its surface. These processes matter because a message that lasted forever would not be communication. It would be a very tiny chemical monologue. Through synapses, the nervous system decides which signals are amplified, softened, blocked, repeated, or ignored. That is how a sensation can become important, how a movement can begin, how a reflex can be shaped, how breathing can be adjusted, and how attention can settle on one thing while the rest of the world fades gently into the background. The body is quietly run through countless chemical decisions, happening in tiny spaces too small to feel, yet powerful enough to shape every moment of experience. Running down the back, protected inside the spine, is one of the most important communication routes in the body. The spinal cord is often imagined as a kind of cable, carrying messages between the brain and everything below it. That picture is useful, but only up to a point. The spinal cord is indeed a major information highway, but it is not a passive bundle of wires. It receives signals, sorts them, responds to some of them locally, and helps coordinate the body with a quiet intelligence of its own. The spinal cord belongs to the central nervous system, along with the brain. It begins at the base of the brainstem and travels downward through the vertebral column, the stacked bones of the spine. These bones do more than help hold the body upright. They form a protective tunnel around the delicate nervous tissue within. Around the spinal cord are protective membranes called the meninges, and around it flows cerebrospinal fluid, which helps cushion, nourish, and chemically support the central nervous system. It is a careful arrangement because the tissue inside is soft, complex, and not especially interested in being knocked about. From the spinal cord, pairs of spinal nerves branch outward to the body. These nerves are part of the peripheral nervous system, carrying information between the central nervous system and the limbs, trunk, skin, muscles, blood vessels, glands, and organs. Each spinal nerve is like a local route joining the main highway. Some carry messages from the body inward, others carry instructions outward. Most contain both, because the body rarely does anything in just one direction. A key part of this organization is the difference between dorsal roots and ventral roots. Sensory information generally enters the spinal cord through the dorsal roots. These incoming signals may carry news from the skin, muscles, joints, or organs. They might report pressure, stretch, pain, temperature, vibration, or the position of a limb. Motor commands generally leave through the ventral roots, travelling outward toward muscles and glands. So, in a broad and useful way, the dorsal side brings information in, while the ventral side sends action out. Inside the spinal cord, there is grey matter and white matter. The grey matter contains many neuron cell bodies, dendrites, and synapses, making it a place where signals can be processed and connected. In cross-section, it has a shape often compared to a butterfly, although admittedly a very serious biological butterfly with no interest in flowers. The white matter surrounds much of this grey matter and contains long myelinated axons. These axons carry information up and down the spinal cord, linking different levels of the body with the brain. The pathways carrying information upward are called ascending tracts. They bring sensory information toward the brain, including touch, pain, temperature, vibration, and body position. The pathways carrying instructions downward are called descending tracts. They help send motor commands from the brain toward the spinal cord and then onward to muscles. Together, these tracts allow the nervous system to build a constant conversation between what the body senses and what the body does. But the spinal cord does more than pass messages along. It can also organize rapid responses without waiting for conscious thought. Reflexes are the clearest example. If the hand touches something painfully hot, sensory signals can enter the spinal cord and help activate motor neurons that pull the hand away before the brain has fully formed the experience of pain. The brain is still informed, of course, usually with a very convincing message along the lines of, "That was a poor decision." But the first protective movement can begin in the spinal cord. The British neurophysiologist Charles Sherrington helped shape modern understanding of this coordinated nervous system. His work on reflexes, integration, and motor control showed that the nervous system does not function as scattered pieces acting separately. It coordinates activity across circuits. Sherrington studied how reflexes are organized, how muscles are controlled, and how the nervous system integrates many signals into purposeful action. His work helped establish the idea that movement and reflexes are not crude automatic twitches, but structured patterns within a larger system of control. This matters because the spinal cord is both a root and a regulator. It carries signals between the brain and body, but it also contains local circuits that help with posture, reflexes, walking patterns, and basic coordination. The body does not wait for the brain to micromanage every muscle fibre. If it did, ordinary movement would be far too slow and clumsy. The spinal cord handles some of the work close to where it is needed, which is a very sensible arrangement for a body that has to remain upright, responsive, and occasionally capable of avoiding coffee tables in dim rooms. Spinal cord injuries can have very different effects depending on where the injury occurs and how severe it is. Because different levels of the spinal cord connect with different regions of the body, damage higher up can affect more functions than damage lower down. Some injuries interrupt movement, sensation, autonomic control, or combinations of these. The exact effects depend on which pathways are damaged, whether signals are partly preserved, and how much communication remains between the brain, spinal cord, and body. The spinal cord shows that the body is not run by the brain alone. The brain is deeply important, but it works with a distributed system. Messages rise and fall through the spinal cord. Reflexes are shaped there. Sensory information is filtered there. Motor commands are organized there. Beneath every smooth step, every quick withdrawal, every small postural adjustment, and every quiet signal from the body, the spinal cord is helping keep life coordinated. It is the highway, the relay station, and the local control center, all hidden inside the calm architecture of the spine. Some of the body's quickest decisions happen before thought has time to put on its shoes. A fingertip touches something hot, and the hand pulls away. A speck moves toward the eye, and the eyelid snaps shut. Something irritates the throat, and a cough arrives with all the politeness of a door being kicked open. These are reflexes, fast, automatic responses that help protect the body, stabilize it, and keep it working when slow deliberation would be a little too slow. A reflex is not a sign that the nervous system has stopped thinking. It is a sign that the nervous system has placed certain jobs close to where they are needed. Conscious awareness is wonderful for planning, imagining, remembering, and deciding whether a second biscuit is a reasonable life choice. But it is not always the best tool for immediate protection. If the body had to hold a meeting every time the foot slipped, the meeting would probably take place on the floor. The basic pathway of a reflex is called a reflex arc. It begins with a sensory receptor, a specialized structure that detects a change. That change might be heat, pressure, stretch, irritation, or pain. The sensory receptor sends information along a sensory neuron toward the spinal cord or brainstem. Inside the central nervous system, that signal may pass through one or more connecting neurons, where it is integrated and shaped into a response. Then a motor neuron carries a command outward to an effector, which is usually a muscle or gland. The effector then does something. A muscle contracts, a limb moves, an eyelid closes, or a secretion changes. This basic idea is beautifully simple, but real reflexes can be surprisingly sophisticated. They are not primitive leftovers from a less impressive version of the body. They are essential control systems. Reflexes protect tissues from damage, help maintain posture, support balance, stabilize vision, regulate breathing, clear the airways, and adjust muscle tone. They keep the body from needing conscious permission for every small correction. In daily life, this is enormously useful, because standing upright is already complicated enough without having to consciously supervise every ankle, knee, hip, shoulder, and eyelash. One familiar example is the knee-jerk reflex, also called the patella reflex. When a doctor taps the tendon just below the kneecap, the tap briefly stretches the quadriceps muscle at the front of the thigh. Inside that muscle are sensory structures called muscle spindles, which detect stretch. They send a signal into the spinal cord, where sensory neurons help activate spinal motor neurons. Those motor neurons then send signals back to the quadriceps, causing it to contract and the lower leg to kick forward slightly. This is a stretch reflex, and it helps the nervous system maintain muscle length and posture. The knee-jerk reflex is often used in medical examinations because it gives a simple clue about the health of certain nerves, spinal cord pathways, and muscles. But in ordinary life, stretch reflexes are constantly helping the body stay stable. When the body sways slightly while standing, muscles are stretched, and reflexes help correct the movement. The adjustments are usually so small and so fast that they never become conscious. The body simply remains upright, as though stillness were easy. It is not. Stillness is a quiet achievement. Withdrawal reflexes are more obviously protective. If the hand touches something sharp or painfully hot, pain receptors in the skin send signals into the spinal cord. Local circuits can activate motor neurons that contract flexor muscles, pulling the hand away. At the same time, opposing muscles may be inhibited so they do not fight against the movement. The result is quick, coordinated escape from danger. The brain is still informed, and the pain becomes conscious, but the first movement can begin before awareness has fully caught up. There is also the crossed extensor reflex, which is especially useful in the legs. If one foot steps on something painful, the nervous system may pull that foot away while activating muscles in the opposite leg to support body weight. So one limb withdraws, while the other helps keep balance. This is not a random flinch. It is a coordinated protective pattern. The nervous system is not merely saying move away. It is also saying, and try not to collapse while doing it, which is thoughtful. Charles Sherrington, the British neurophysiologist, helped explain how reflexes fit into the wider organisation of the nervous system. His work showed that reflexes are not isolated little sparks of activity, but coordinated patterns shaped by integration. One of his important ideas was reciprocal innovation. This means that when one muscle group is activated, an opposing muscle group can be inhibited. For example, bending the arm works more smoothly when the muscles that bend the elbow contract, while the muscles that straighten it relax. Without this balance, movement would become stiff, awkward, and far less graceful. The body would not glide through motion so much as negotiate with itself at every joint. Reflexes reveal something fundamental about how the body's run. Many actions feel immediate because the nervous system is built to act before slow, conscious thought would be useful. Blinking protects the eyes. Coughing helps clear the airways. Postural reflexes keep the body balanced. Withdrawal reflexes protect tissues. Stretch reflexes stabilize muscles. These responses are not separate from intelligence. They are part of biological intelligence, written into circuits that work quickly, quietly, and usually without applause. The body is therefore not guided only by deliberate decisions. It is also guided by fast protective loops beneath awareness, constantly adjusting, correcting, guarding, and stabilizing. Consciousness receives the polished version of events, while much of the nervous system's work has already begun. Beneath ordinary experience, reflexes help keep the body safe enough, steady enough, and organized enough for thought to arrive a moment later and take the credit. At the base of the brain, where the soft complexity of thought narrows into the long column of the spinal cord, sits one of the most essential regions of the nervous system. The brainstem is not usually the part that gets poetic attention. It does not have the glamorous reputation of the cerebral cortex, where conscious thought, language, imagination, and planning are often placed. But the brainstem is older, deeper, and in many ways more urgent. It is the quiet survival bridge between the brain and the body. The brainstem links the brain with the spinal cord, carrying signals upward and downward. But it also does far more than pass messages along. It helps regulate basic functions that life depends on from moment to moment. Breathing, heart rate, blood pressure, swallowing, wakefulness, pupil responses, eye movements, coughing, sneezing, vomiting, and many other reflexive actions all involve brainstem circuits. It is not the whole control system by itself, but it is one of the main places where the body keeps its essential rhythms from drifting into chaos. The brainstem is usually divided into three main parts: the midbrain, the pons, and the medulla oblongata. The midbrain is involved in eye movements, visual and auditory reflexes, motor control, and alertness. It helps coordinate how the eyes move and how the body responds to sudden sights and sounds. The pons sits below the midbrain and acts as a kind of bridge between different regions, including the cerebrum and the cerebellum. It is involved in breathing regulation, sleep, facial sensation, facial movement, and the coordination of signals that help the body stay responsive and balanced. The medulla oblongata lies lowest, closest to the spinal cord, and it is especially important for breathing, heart rate, blood pressure, swallowing, coughing, and other vital reflexes. This is why the brainstem has such a serious reputation in medicine. Damage to this region can be extremely dangerous because it can disturb functions that cannot simply be postponed. The body can manage without solving a puzzle for a while. It cannot casually reschedule breathing until next Thursday. The point is not to make the brainstem sound frightening, but to appreciate its quiet importance. Much of what it does is so constant that it disappears from awareness, which is often how the most essential biology works. Breathing is a beautiful example because it sits halfway between choice and automatic control. You can decide to take a slow breath. You can hold your breath for a short time. You can sigh, hum, speak, sing, or deliberately breathe more deeply. But when attention wanders, breathing continues. During sleep, breathing continues. While thinking about something else entirely, breathing continues. The nervous system allows breathing to be partly voluntary, but it does not trust consciousness with the whole job, which is wise, considering consciousness occasionally forgets why it opened the fridge. A key brainstem region involved in generating breathing rhythm is the pre-Butzinger complex, located in the medulla. This network of neurons helps produce the rhythmic pattern that underlies breathing. It does not work alone, because breathing is shaped by many signals, including carbon dioxide levels, oxygen levels, blood acidity, emotional state, physical activity, and input from the lungs and airways. But the pre-Butzinger complex is one of the crucial rhythm generators. It helps give breathing its repeating pattern, the quiet rise and fall that continues beneath thought. The brainstem also helps regulate heartbeat and blood pressure. One way it does this is through feedback from baroreceptors, which are pressure-sensitive receptors located in places such as the carotid sinus in the neck and the aortic arch near the heart. These receptors detect stretch in the walls of blood vessels, which reflects changes in blood pressure. When blood pressure rises, baroreceptors send more signals to the brainstem. The brainstem can then adjust autonomic output, helping slow the heart or relax blood vessels. When blood pressure falls, the pattern changes, and the body can respond by increasing heart rate or tightening blood vessels. It is a constant balancing act, like a quiet internal thermostat, except instead of temperature alone, it is helping manage the pressure that moves blood through the body. A major pathway in this internal communication is the vagus nerve. The vagus nerve carries signals between the brainstem and many organs, including the heart, lungs, and digestive tract. It is a key part of the parasympathetic nervous system, which helps support rest, digestion, and recovery. It also carries sensory information from internal organs back toward the brainstem, giving the nervous system news from inside the body. The vagus nerve does not simply tell the body to calm down, as it is sometimes oversimplified to do. It is a complex two-way pathway involved in heart regulation, breathing patterns, digestion, reflexes, inflammation-related signaling, and the subtle sensing of internal bodily state. Swallowing also depends on brainstem coordination. It feels simple because it happens so often, but swallowing requires precise timing between the mouth, throat, airway, and esophagus. The nervous system has to move food or liquid downward while protecting the airway. Coughing, gagging, and sneezing are similarly coordinated protective responses. They may not feel elegant, especially when they arrive in public at exactly the wrong moment, but they are signs of a nervous system trying to defend the body's entrances and exits with admirable commitment. The brainstem also contributes to wakefulness through networks sometimes described as the ascending arousal system. These circuits help maintain alertness and influence the transition between sleep and waking. This means that consciousness itself depends, in part, on deeper systems that regulate whether the brain is awake enough to experience the world clearly. The most sophisticated thought still rests on ancient machinery keeping the lights on. The brainstem shows how much of life is handled beneath deliberate control. The body does not ask permission before adjusting blood pressure. It does not wait for conscious approval before swallowing safely, changing breathing rhythm, slowing the heart during rest, or producing a cough when the airway is irritated. Conscious attention usually notices these functions only when something changes: a racing pulse, a held breath, a dizzy moment, a sudden cough, a swallow that goes slightly wrong. Most of the time, the brainstem works in the background with remarkable steadiness. It is not dramatic. It is not showy. It simply helps keep the body alive from one breath to the next. Beneath thought, beneath decision, beneath the quiet surface of rest, the nervous system is already working, regulating the rhythms that make every other experience possible. Inside the body, there is a quiet set of background settings that is being adjusted all the time. The pupils widen or narrow, blood vessels tighten or relax, sweat glands become more or less active, The stomach speeds up, slows down, or waits patiently for a better moment. The bladder sends signals about fullness. The heart changes its rhythm. The lungs alter their pattern. Glands release substances that shift the body's state. Most of this happens without needing conscious permission, which is fortunate, because trying to manually supervise every gland would be a full-time job with terrible working conditions. This background regulation is handled largely by the autonomic nervous system. The word autonomic suggests something self-governing, and that is a useful clue. The autonomic nervous system is the division of the nervous system that helps regulate internal body functions. It controls smooth muscle, cardiac muscle, and glands. Smooth muscle is found in places such as blood vessel walls, airways, the digestive tract, and the bladder. Cardiac muscle is the specialized muscle of the heart. Glands produce secretions including sweat, saliva, digestive fluids, and other chemical substances. Through these targets, the autonomic nervous system can alter the physical state of the whole body very quickly. It is common to divide the autonomic nervous system into the sympathetic nervous system and the parasympathetic nervous system. These are often described as opposites, and in some ways they do push the body in different directions. But it is misleading to imagine one as the villain and the other as the hero. The sympathetic nervous system is not simply bad, and the parasympathetic nervous system is not simply good. They are complementary systems, each useful in the right circumstances. A healthy body needs both readiness and recovery. It needs the ability to act and the ability to settle. It needs to spend energy, and it needs to conserve it. The sympathetic nervous system is strongly associated with readiness. When the body needs to respond to challenge, effort, uncertainty, cold, excitement, pain, or danger, sympathetic activity can increase. The heart may beat faster and more forcefully. Blood vessels in some regions may narrow, while blood flow is redirected towards skeletal muscles and away from processes that are less urgent in the moment. The pupils may widen. Sweating may increase. The airways can open more fully. Stored energy can be mobilized, helping make fuel available to working tissues. This does not only happen during dramatic fear. It can happen during exercise, concentration, public speaking, standing up quickly, or realizing that the oven was left on, which is a very efficient way to become suddenly alert. The parasympathetic nervous system is strongly associated with rest, digestion, and recovery. It helps slow the heart rate, supports salivation, stimulates digestive activity, and encourages energy conservation. Much of its influence travels through the vagus nerve, though the parasympathetic system also includes other pathways. When the body is safe enough to digest, repair, and settle, parasympathetic activity becomes especially important. It helps shift the body away from mobilization and toward maintenance. This is not laziness. It is biological housekeeping. Digestion, immune function, restoration, and tissue repair are not passive states. They are quiet work. One of the major figures in understanding internal regulation was Walter Cannon, an American physiologist who helped develop the concept of homeostasis. Homeostasis refers to the body's ability to maintain relatively stable internal conditions, such as temperature, blood chemistry, and blood pressure, even while the outside world changes. Cannon also described the fight or flight response, the coordinated set of changes that prepares an animal to confront or escape a threat. That phrase is still useful, but the full stress response is broader than one dramatic alarm. The body can freeze, orient, monitor, recover, adapt, conserve energy, or prepare for action in different ways depending on the situation. The autonomic nervous system does not work alone. It interacts with hormones, immune signals, the brainstem, the hypothalamus, the spinal cord, sensory systems, and emotional circuits. For example, the hypothalamus helps link the nervous system with the endocrine system through the pituitary gland. The brainstem helps regulate breathing, heart rate, blood pressure, swallowing, and other survival functions. Sensory feedback from the body tells the nervous system what is happening inside, so adjustments can be made. This is not a simple command being sent from the brain to the organs. It is a loop of information, correction, and response. The digestive system has its own remarkable network called the enteric nervous system. This semi-independent network is embedded in the wall of the digestive tract and helps coordinate movement, secretion, local blood flow, and digestive reflexes. It contains a very large number of neurons and can carry out many functions without direct instruction from the brain. This is why it is sometimes nicknamed the second brain. The nickname is memorable, but it should be handled carefully. The enteric nervous system is not a thinking brain. It is not sitting in the gut forming opinions about your life choices, although after certain meals it may seem to have feedback. It is a specialized control network built to manage the complex work of digestion. Together, these systems show how quietly the nervous system runs the body. A change in posture can alter blood pressure, and autonomic circuits respond. A stressful thought can change heart rate and breathing. A meal can shift blood flow and digestive activity. A warm room can increase sweating. Darkness can alter pupil size. A safe, restful moment can let the body soften into recovery. These adjustments are usually felt only as mood, comfort, tension, hunger, warmth, tiredness, or calm. The autonomic nervous system is therefore not just background machinery. It is one of the main ways the body becomes ready, settled, energized, guarded, restored, or alert. It changes the body before thought fully catches up. It prepares the internal world for what the organism seems to need. Beneath ordinary awareness, the nervous system is constantly turning tiny biological dials, keeping life balanced enough for the next breath, the next heartbeat, and the next quiet moment of rest. The body is constantly gathering news from the world. Some of that news is obvious, like the feeling of a hand resting on a blanket, the warmth of a mug, or the pressure of a foot against the floor. Some of it is quieter, like the stretch of a muscle, the angle of a joint, or the small adjustments that keep the body balanced while standing still. These signals belong to a broad sense called somatosensation, which is the nervous system's ability to detect touch, pressure, vibration, temperature, pain, body position, and movement. Somatosensation is not one single sense. It is a family of senses working together through the skin, muscles, joints, tendons, spinal cord, and brain. The skin can detect fine touch, deep pressure, vibration, warmth, cold, and painful stimulation. Muscles and tendons report stretch and tension. Joints help signal position and movement. Together, these systems allow the body to know where it is, what it is touching, and how it is changing from moment to moment. In the skin, different receptors respond best to different kinds of information. Merkel cells are especially important for steady pressure and fine detail, helping the nervous system detect edges, shapes, and texture. Meissner corpuscles respond well to light touch and fluttering movement across the skin, especially in sensitive areas such as the fingertips. Pacinian corpuscles detect deep pressure and rapid vibration, making them useful for sensing fast mechanical changes. Ruffini endings respond to skin stretch and sustained pressure, helping with the sense of hand position and object grip. These receptors do not simply send identical messages. Each one listens for a slightly different feature of contact, like a quiet team of specialists taking notes on the physical world. This is why touch can feel so rich. A surface can be smooth, rough, sharp, soft, sticky, warm, cold, steady, moving, vibrating, or pressing. The nervous system builds these experiences from patterns of receptor activity. A fingertip touching velvet sends a different pattern from a fingertip touching sandpaper. Holding a cup sends a different pattern from brushing against a sleeve. Even a very ordinary object becomes a complicated sensory event once the nervous system begins translating pressure, texture, temperature, and movement into experience. The body also has a sense that is often unnoticed until it fails or is tested. This is proprioception, the sense of body position and movement. Proprioception tells the nervous system where the limbs are without needing to look. It depends on muscle spindles, Golgi tendon organs, and joint receptors. Muscle spindles detect changes in muscle length and how quickly that length is changing. Golgi tendon organs detect tension in tendons, helping monitor force. Joint receptors contribute information about joint position and movement, especially near the limits of motion. Proprioception is why a person can close their eyes and touch a finger to the nose. It is why walking does not require staring down at every step like a cautious robot testing a new software update. It is why the hand can reach behind the head, scratch an itch, or find a pocket without needing a live video feed from the eyes. Vision helps movement, of course, but proprioception gives the nervous system an internal map of the body's position. If proprioceptive feedback disappeared, ordinary movement would become strangely difficult. Standing upright would require enormous visual concentration. Walking across a room would become uncertain and effortful. Reaching for a glass would need constant checking, because the brain would no longer receive reliable updates about where the arm and hand were in space. It would be a little like trying to control a puppet from the inside while someone had switched off most of the string's position sensors. Possible in some limited ways, perhaps, but not smooth, natural, or relaxing. Once sensory information enters the nervous system, it travels through organized pathways. Fine touch, vibration, and proprioception often travel through the dorsal column medial lemniscus pathway. In broad terms, signals enter the spinal cord, travel upward, cross over in the brainstem, pass through the thalamus, and reach the somatosensory cortex. Pain and temperature often travel through the spinothalamic pathway. These signals usually enter the spinal cord, cross over relatively early, and then ascend toward the thalamus and brain. The details are complex, but the larger idea is clear. The nervous system has dedicated routes for carrying different kinds of bodily information. The thalamus acts as a major relay station for many sensory signals, helping route information toward the cerebral cortex. The somatosensory cortex, located in the parietal lobe, contains an organized map of the body. Some body parts, such as the lips, fingers, and tongue, take up a large amount of cortical space because they are especially sensitive and require fine control. This body map is sometimes illustrated as the sensory homunculus, a strangely distorted little figure with enormous hands and lips. It looks faintly alarming, but it reveals something useful. The brain represents the body according to sensory importance, not according to polite portrait standards. Sensation is not a direct copy of the outside world, it is a processed signal. Receptors respond to physical changes, pathways carry information, and the brain interprets those signals in context. Attention matters, expectation matters, previous experience matters. A light touch may feel comforting in one situation and irritating in another. Cold air may feel refreshing or unpleasant depending on mood, temperature, and what the body was expecting. The nervous system does not simply record reality like a camera. It constructs a usable version of reality from signals that are filtered, compared, and interpreted. This quiet construction is happening almost all the time. The nervous system monitors the pressure under the feet, the angle of the neck, the stretch of the back, the warmth of the skin, the position of the hands, and the movement of the limbs. Most of this never becomes a clear thought. It remains in the background, supporting balance, posture, movement, comfort, and safety. So the body is not run only by dramatic commands from the brain. It is run through constant sensory updating. Touch tells the nervous system what meets the skin. Proprioception tells it where the body is. Pain and temperature warn of possible danger. Pressure and vibration add detail to the physical world. Beneath awareness, the nervous system quietly maintains an internal map, allowing the body to move through life without needing to stop and consciously calculate itself at every step. Pain is one of the nervous system's most powerful warning systems, and also one of its strangest. It can arrive suddenly, sharply, and with complete confidence, as though the body has just received urgent news and would like everyone to stop what they are doing. But pain is not a simple measuring device for tissue damage. It is a protective experience generated by the nervous system. That does not mean pain is imaginary. Pain is very real. It means that pain is the brain and body's way of judging threat, using signals from tissues, memories, context, attention, emotion, and past experience. The specialized sensory neurons involved in detecting possible harm are called nociceptors. These neurons respond to potentially damaging mechanical, thermal, or chemical stimuli. Mechanical stimuli might include crushing, cutting, or strong pressure. Thermal stimuli include heat or cold intense enough to threaten tissue. Chemical stimuli can come from inflammation, injury, or irritating substances released in damaged areas. Nociceptors do not technically send pain itself. They send danger-related signals. Pain is the experience the nervous system may create after interpreting those signals. This distinction matters because the body is not only asking, is there damage? It is also asking, how dangerous is this? What does it mean? And what should be done about it? A small cut noticed in a calm moment may hurt mildly. The same kind of injury during panic, exhaustion, or fear may feel much worse. A bruise discovered after an exciting event may barely be noticed until later, when the nervous system finally has a quiet moment to file its complaint. Pain is protective, but like many protective systems, it is not always perfectly proportionate. There are different routes for pain-related information. Fast pain is often carried by myelinated A delta fibers. These fibers send signals relatively quickly, and are associated with the sharp, immediate pain that helps locate a threat. This is the sudden sting after touching something sharp, or the bright warning that arrives just after a burn. Slow pain is often carried by unmyelinated C fibers. These signals travel more slowly and are associated with dull, aching, throbbing, or burning pain that can linger. Together, these systems give the nervous system both a quick alarm and a longer-lasting reminder that an area may need protection. Pain signals enter the spinal cord, where they can be strengthened, weakened, redirected, or combined with other information. This was one of the major insights behind the gate control theory of pain, proposed by Ronald Melzack and Patrick Wall in the 1960s. Their theory changed the understanding of pain by showing that pain signals are not simply passed upward like messages through a tube. The spinal cord can modulate them. Signals from touch fibers, descending signals from the brain, and local spinal circuits can all influence how much pain-related information continues upward. This helps explain why rubbing a bumped elbow can make it feel slightly better. Touch signals can interact with pain pathways in the spinal cord, changing the flow of information. It does not magically erase the injury, but it can reduce the intensity of the warning. The nervous system apparently sometimes appreciates a little comforting admin. Pain involves many regions of the nervous system. The spinal cord helps process incoming signals. The brainstem contributes to arousal, reflex responses, and descending control. The thalamus acts as a major relay station, directing signals toward different parts of the brain. The somatosensory cortex helps identify where the pain is and what kind of sensation it may be. The insula is involved in the internal feeling of the body and the unpleasantness of pain. The anterior cingulate cortex contributes to attention, emotional distress, and motivation to respond. The prefrontal cortex helps interpret meaning, expectation, decision-making, and control. Pain is not located in one single pain center. It is built by a network. The brain can also turn pain signals up or down through descending pain modulation. Pathways from the brainstem and higher brain regions can influence the spinal cord, changing how strongly incoming danger signals are transmitted. This can be useful. During an emergency, pain may be temporarily reduced so the body can escape danger. During rest, worry, uncertainty, or repeated threat, the same system may become more sensitive. Attention matters too. Focusing intensely on a painful area can make it feel louder. Feeling safe, distracted, supported, or calm can sometimes soften it. None of this makes pain fake. It shows that pain is an active interpretation, not a passive recording. Chronic pain reveals the protective system at its most difficult. Sometimes pain persists after tissues have healed, or continues at a level that no longer matches the original injury. This can happen because the nervous system has become sensitized. Sensitization means pain pathways have become more responsive, so signals are amplified and ordinary input may feel threatening. The spinal cord, brain, immune signals, and stress systems can all contribute. This is not weakness, exaggeration, or a failure of character. It is a nervous system problem where the warning system has become overprotective. A smoke alarm is useful when there is a fire, but if it becomes too sensitive, it may scream about toast, steam, or absolutely nothing obvious at all. Pain can work in a similar way. Its purpose is protection, but protection can become excessive. The body may keep guarding, bracing, and warning, even when the original danger has changed. Understanding this does not remove the suffering, but it can make the suffering less mysterious and less morally loaded. Pain, then, is one of the clearest examples of how the nervous system quietly runs the body. It warns, protects, prioritizes, interrupts, and demands action. It can save tissue from harm and teach the body to avoid danger. It can also become painfully overcautious. Beneath awareness, the nervous system is constantly judging threat, shaping warning signals, and deciding what must be noticed. Pain is not merely damage speaking. It is protection speaking, sometimes wisely, sometimes too loudly, but always from within the strange logic of a body trying to keep itself safe. Movement can feel wonderfully simple from the inside. A hand reaches for a cup. A foot steps over a cable. The head turns toward a sound. The eyelids blink, the throat swallows, the fingers adjust their grip, and the body carries on as though all of this were easy. But voluntary movement is not a single command travelling from the brain to a muscle. It is a coordinated process involving planning, timing, feedback, correction, prediction, and control. Even the smallest movement is less like pressing a button and more like conducting a very quiet orchestra, where most of the musicians are hidden under the floorboards. The process begins across several regions of the brain. The primary motor cortex, located in the frontal lobe, is heavily involved in sending movement commands down toward the spinal cord. The premotor cortex helps prepare movements in response to sensory information, such as reaching towards something seen or heard. The supplementary motor area is involved in internally planned actions and sequences, including movements that are organized without an obvious outside cue. These cortical regions do not work alone. They are part of wider loops involving the basal ganglia, the cerebellum, the brainstem, the spinal cord, sensory systems, and the muscles themselves. The brain has to solve a surprisingly difficult problem every time the body moves. It must decide what action is needed, which muscles should be involved, how strongly they should contract, in what order they should activate, and how to adjust if the world is slightly different from expected. A cup may be heavier than it looks, the floor may be uneven, a step may be shorter than intended. The body may be tired, tense, or distracted. Movement depends on constant feedback from vision, touch, proprioception, and the inner ear, with corrections made almost continuously. Once motor commands travel downward from the brain, they pass through pathways in the brainstem and spinal cord. Some commands travel through major descending pathways that influence spinal motor neurons. These spinal motor neurons are the final nerve cells that directly communicate with skeletal muscles. A motor neuron and the muscle fibers it controls are called a motor unit. When that motor neuron fires, the muscle fibers in its motor unit contract. Motor units vary depending on the kind of movement required. Fine movements, such as controlling the fingers or adjusting the eyes, need small motor units where each motor neuron controls relatively few muscle fibers. This allows precise control. Powerful movements, such as pushing through the legs or lifting something heavy, often use larger motor units, where one motor neuron controls many more muscle fibers. A hand threading a needle and a leg climbing stairs are both movements, but they ask for very different patterns of control. The nervous system, sensibly, does not use the same setting for embroidery and emergency sofa lifting. The place where a motor neuron communicates with a skeletal muscle fiber is called the neuromuscular junction. When an electrical signal reaches the end of the motor neuron, it triggers the release of acetylcholine. This neurotransmitter crosses the tiny gap and binds to receptors on the muscle fiber. That chemical message starts an electrical change in the muscle membrane, leading to a chain of events inside the muscle that allows contraction. In simple terms, a nerve signal becomes a muscle action through the carefully timed release of acetylcholine. Muscle contraction itself depends on structures inside muscle fibers, including actin and myosin filaments that slide past one another. The nervous system does not need to consciously manage every microscopic detail. It sets patterns of activation, and the muscle machinery carries out the contraction. This division of labour is rather elegant. The brain does not personally supervise every protein. It has enough to be getting on with. Smooth movement depends heavily on the cerebellum. The cerebellum sits at the back of the brain and is deeply involved in coordination, balance, timing, error correction, and prediction. It compares intended movement with actual movement, helping adjust actions so they become smoother and more accurate. If a hand reaches too far, too slowly, or with the wrong force, cerebellar circuits help refine the next attempt. The cerebellum is also important for motor learning, which is why repeated practice can turn awkward effort into fluid skill. Riding a bicycle, playing an instrument, typing, walking steadily, or catching a ball all depend on the nervous system learning how movement should feel and adjusting when it does not match expectation. The basal ganglia play a different but equally important role. These deep brain structures are involved in action selection, habit, movement initiation, and the suppression of unwanted movement. They help the nervous system choose one action while holding back others. This matters because the body is full of possible movements at every moment. Standing up, scratching an arm, looking left, shifting weight, speaking, stepping forward, or staying still are all options. The basal ganglia help sort possible action so the body does not try to do everything at once, which would be less graceful movement and more biological jazz accident. The importance of the basal ganglia can be seen in Parkinson's disease, first described in detail by James Parkinson in the early 19th century. Parkinson's disease involves loss of dopamine-producing neurons in a region connected with basal ganglia circuits, particularly the substantia nigra. The result can include slowed movement, stiffness, tremor, and difficulty initiating actions. This shows that movement is not merely a matter of muscles being strong enough. It depends on the brain's ability to select, release, regulate, and smooth the commands that guide the body. The brainstem also contributes to movement, especially posture, balance, eye movements, facial actions, swallowing, and automatic patterns that support voluntary behavior. The spinal cord contains circuits that coordinate reflexes and rhythmic movement patterns. Sensory feedback from muscles and joints tells the nervous system whether the movement is unfolding as intended. The body is constantly checking itself. It sends a command, receives a reply, notices errors, and corrects them, often before conscious awareness has any idea that a correction was needed. Even a simple reach depends on this quiet choreography. The eyes locate the object. The brain estimates distance. The The shoulder lifts, the elbow extends, the wrist adjusts, the fingers open, the hand slows at the right moment, touch receptors report contact, grip force changes, and proprioception updates the arm's position. A blink, a step, a swallow, or a slight shift in posture may feel effortless, but each one depends on prediction, correction, timing, and feedback. Movement is one of the clearest ways the nervous system quietly runs the body, turning intention into action while hiding most of the work beneath the smooth surface of ordinary life. The body does not know where it is through one sense alone. It builds orientation from many streams of information arriving at once. Vision tells the nervous system how the world appears to move around the body. The vestibular system in the inner ear reports how the head is moving. Proprioception tells the brain where the limbs and joints are. Touch tells it how the body meets the ground, a chair, a blanket, or a wall. Hearing adds direction, distance, and warning. Together, these senses create the quiet feeling of being located somewhere, facing a certain way, balanced enough to remain upright, and ready to move without needing to. Solve a geometry problem every time a foot leaves the floor. The vestibular system is especially important for balance and orientation. It sits deep inside the inner ear, close to the structures used for hearing, and contains the semicircular canals and the otolith organs. The otolith organs include the utricle and the saccule. These delicate structures send information along the vestibular nerve toward the brainstem and cerebellum, where it is combined with signals from vision, muscles, joints, and skin. The result is not usually a conscious sensation. Most of the time, balance simply feels like nothing going wrong, which is one of biology's more underrated achievements. The semicircular canals detect head rotation. There are 3 canals on each side of the head, arranged at different angles so they can detect turning in different directions. Inside them is fluid. When the head rotates, the fluid lags behind slightly because of inertia, bending tiny sensory hair cells. Those hair cells convert mechanical movement into nerve signals, so when the head turns left, nods down, or tilts to the side, the semicircular canals help report that motion. They do not tell the whole story of where the body is, but they are very good at noticing rotation. The otolith organs detect different kinds of movement, the utricle and saccule respond to linear acceleration, and head position relative to gravity. They contain tiny calcium carbonate crystals, often called otoconia, resting on a gel-like layer above sensory hair cells. When the head tilts, or the body accelerates in a straight line, these crystals shift slightly, bending the hair cells and changing nerve signals. This helps the nervous system sense whether the head is upright, tilted, moving forward, rising, falling, or slowing down. It is a wonderfully strange arrangement. Part of balance depends on tiny stones in the inner ear behaving themselves. Most of the time they do, which is very considerate of them. One of the most useful vestibular reflexes is the vestibular ocular reflex. This reflex helps stabilize vision while the head moves. When the head turns in one direction, the eyes automatically move in the opposite direction to keep the gaze steady. Without this reflex, the world would blur and bounce whenever the head moved. Reading a sign while walking would become difficult. Looking across a room while turning the head would feel unstable. The vestibulo-ocular reflex is why the view can remain steady even while the body is in motion. It is a small piece of nervous system engineering that quietly keeps the visual world from behaving like a badly held camera. Hearing also begins in the inner ear, though it uses different structures. Sound starts as vibration moving through air. Those vibrations enter the ear, move the eardrum, and pass through the small bones of the middle ear into the cochlea. The cochlea is a spiral-shaped structure filled with fluid and lined with specialized hair cells. Different regions of the cochlea respond best to different sound frequencies. When fluid movement bends the hair cells, mechanical vibration is transformed into nerve signals. These signals travel along the auditory nerve toward the brainstem, thalamus, and auditory cortex. From there, the nervous system can interpret pitch, loudness, rhythm, speech, direction, and the many tiny clues that make a sound feel near, distant, familiar, or unexpected. Vision is also a nervous system process from the beginning. Light enters the eye and reaches the retina, a thin layer of nervous tissue at the back of the eye. The retina contains rods and cones. Rods are especially useful in dim light and are highly sensitive to brightness. Cones support colour vision and fine detail, especially in brighter conditions. These photoreceptors influence networks of retinal cells, and the final output leaves through retinal ganglion cells. Their axons form the optic nerve, carrying visual information toward the brain. Signals pass through the thalamus, especially a region called the lateral geniculate nucleus, before reaching the visual cortex in the occipital lobe. So vision is not simply a picture entering the head. The eye begins processing information before it ever reaches the brain's visual cortex. The nervous system detects contrast, edges, motion, colour, brightness, and patterns, then builds a usable visual world from those signals. The brain combines vision with vestibular input and proprioception to decide how the body is moving through space. When these systems agree, orientation feels easy. When they disagree, things can become uncomfortable. Motion sickness is one example. It can happen when the inner ear reports movement, but the eyes do not see matching motion, or when visual motion suggests movement that the vestibular system does not confirm. Standing in the dark offers another example. With less visual information available, the body relies more heavily on vestibular signals, proprioception, and touch from the feet. Dizziness can arise when the brain receives confusing or mismatched information about motion and position. Balance is not one simple sense. It is a negotiated agreement between several systems, and like many negotiations, it becomes noticeable mainly when someone at the table starts disagreeing. Most of the time, this agreement works beautifully. The nervous system quietly knows which way the head is turned, where the ground is, how the body is leaning, what the eyes are seeing, what the ears are hearing, and how the limbs are positioned. It keeps the gaze steady, the posture adjusted, and the body oriented in space without making balance feel like an active calculation. Beneath every calm step, every glance across a room, every turn of the head, and every moment of standing still, the nervous system is silently asking where the body is, what is moving, and how to keep the world steady enough to live in. Emotion is sometimes described as if it lives only in the mind, like a private weather system drifting through thought. But emotion is not just a vague feeling floating somewhere behind the eyes. It is a body-brain process. It involves physiology, attention, memory, threat assessment, reward, social meaning, interpretation, and the physical state of the body itself. An emotion can change breathing, heart rate, muscle tension, facial expression, posture, digestion, temperature, pain sensitivity, and the way attention moves through the world. This is why emotion is felt, not merely thought. Anxiety may arrive with a tight chest, a restless stomach, and a sharpened awareness of small sounds. Calm may arrive with slower breathing, softer muscles, and a sense that the room has become a little less demanding. Joy may lift the face and change the rhythm of the body. Grief may feel heavy in the limbs. Embarrassment may warm the skin. The nervous system does not simply label an emotion and leave the body alone. It helps create the physical feeling of being in that emotion. The limbic system is a traditional name for a group of brain regions involved in emotion, memory, motivation, and bodily state. The term is useful, but it can also be a little too tidy. Emotion does not belong to one neat, emotional brain sealed away from the rest. It emerges from interacting networks that include the amygdala, hippocampus, hypothalamus, insula, anterior cingulate cortex, prefrontal cortex, nucleus accumbens, brainstem, and autonomic nervous system. These regions help connect what is happening outside the body, what is happening inside it, and what the situation might mean. The amygdala is often called the fear center, but that phrase is too narrow. The amygdala is better understood as a system involved in detecting relevance, importance, and potential threat. It helps the brain learn which sights, sounds, smells, places, faces, or situations may matter for survival. Fear is one important part of that work, but the amygdala is not simply a tiny panic button. It can be involved in emotional learning, attention, memory, uncertainty, and the detection of signals that deserve a stronger response. It is less like a monster under the bed, and more like a very alert security guard who occasionally overdoes the job. Joseph Ledoux is strongly associated with research on fear circuits and the amygdala. His work helped show how sensory information can influence defensive responses through pathways involving the thalamus, amygdala, and cortex. Earlier descriptions sometimes made this sound like a simple, fast road and slow road for fear, but emotional neuroscience has become more nuanced. The brain does not merely detect fear like a smoke alarm detecting smoke. It evaluates signals through layers of memory, context, bodily state, and interpretation. The hippocampus is especially important for memory and context. It helps link experiences to places, sequences, and circumstances. This is one reason emotional memories can become so strongly tied to a location, a smell, a sound, or a particular time of day. A certain song may bring back a whole period of life. A smell may suddenly reopen a childhood kitchen. A room may feel comforting or uneasy before the reason is fully clear. The hippocampus helps place experience in context, and emotion can make that context more memorable. The nervous system is very good at keeping receipts, even when nobody asked it to. The hypothalamus is another crucial region because it links the nervous system with the endocrine system. It helps regulate hunger, thirst, body temperature, sleep rhythms, stress responses, reproductive functions, and autonomic activity. It also controls the pituitary gland, which releases hormones that influence other glands throughout the body. Through the hypothalamus and pituitary gland, an emotional event can become a whole body event. A thought, memory, or perceived threat can alter hormone release, heart rate, sweating, digestion, and energy mobilization. The body does not always wait for proof before preparing itself. Sometimes a possibility is enough. The insula plays a major role in interoception, which is the nervous system's sensing of internal body signals. These signals include heartbeat, breathing, gut state, temperature, nausea, fullness, discomfort, and the general condition of the body from within. Interoception helps create the felt sense of being alive inside a body. It is part of why emotion can feel located in the chest, throat, stomach, face, or skin rather than floating as a pure idea. The anterior cingulate cortex is also involved in attention, effort, pain, conflict, and the emotional significance of experience. The prefrontal cortex helps with interpretation, planning, impulse control, social judgment and reappraisal, allowing the brain to reconsider what a feeling means rather than simply obeying it. The nucleus accumbens is strongly involved in reward, motivation, reinforcement, and learning what is worth seeking again. It works within circuits that use dopamine, but dopamine should not be reduced to simple pleasure. Dopamine is involved in motivation, prediction, learning, and the difference between what was expected and what actually happened. Reward systems help the nervous system guide behavior toward food, warmth, social connection, curiosity, achievement, and other useful goals. Occasionally they also guide a person toward checking the fridge for the third time, just in case the contents have become more inspiring. Emotion, then, is not separate from bodily control. It is one of the ways the nervous system prepares the body for action, rest, defense, connection, withdrawal, attention, or recovery. A feeling is not only a message to the mind, it is a change in the whole organism. Muscles shift, organs respond, hormones move, attention narrows or widens, memories become more available, and the body takes on a particular state. This connects directly to the quiet work of the nervous system. The body is not run only through obvious commands like move this hand or take that step. It is also run through the changing physical feeling of being alive. Emotion helps decide what matters, what is safe, what is uncertain, what is worth approaching, and what should be avoided. Beneath the surface of thought, the nervous system is constantly blending memory, sensation, internal signals, and meaning, turning biology into the felt experience of a moment. Stress has a rather unfair reputation, partly because the word is often used only when something feels unpleasant, overwhelming, or slightly too much for a Tuesday. But stress in biology is not automatically harmful. It is a coordinated response that prepares the body to meet demands. Those demands might be danger, exercise, cold, injury, uncertainty, public speaking, an urgent deadline, or the sudden realization that an email was sent with the attachment missing. The nervous system does not treat all of these situations as identical, but it does have a set of internal tools for shifting the body into a more prepared state. At its simplest, stress is about adjustment. The body detects that something requires effort, attention, protection, or adaptation, and it changes its internal settings. Heart rate may rise, breathing may become faster or shallower, muscles may tense, attention may narrow, digestion may slow, energy may be released into the bloodstream, sensory systems may become more alert. None of this is necessarily bad. In the right amount at the right time, stress can be useful. It helps a person run, focus, speak, compete, solve problems, respond quickly, and survive. A body with no stress response at all would not be peaceful. It would be dangerously underprepared. One of the fastest stress systems is the sympathetic adrenal medullary system. This involves the sympathetic nervous system and the adrenal medulla, the inner part of the adrenal glands, which sit above the kidneys. When the brain and body detect a demand that requires rapid readiness, sympathetic nerves can activate the adrenal medulla. The adrenal medulla releases adrenaline and norepinephrine into the bloodstream. These chemicals help produce many of the familiar signs of acute stress: a faster heartbeat, increased blood pressure, widened airways, greater alertness, and the mobilization of energy. Adrenaline and norepinephrine are not simply panic chemicals. They are readiness chemicals. They help the body prepare for action. During exercise, they support physical effort. During danger, they help mobilize escape or defense. During concentration, they can sharpen attention. They alter how the body distributes blood, making more available to skeletal muscles and the heart, while digestion may become less active for a while. This is sensible in a short-term challenge. If a person needs to sprint away from something threatening, the body is not especially concerned with digesting lunch in a calm and leisurely manner. The sandwich can wait. The legs have a more urgent memo. A slower but deeply important stress system is the hypothalamic pituitary adrenal axis. This begins in the hypothalamus, a small but powerful region of the brain involved in hunger, temperature, sleep rhythms, autonomic control, and hormone regulation. When a stress response is needed, the hypothalamus signals the pituitary gland, which sits beneath the brain. The pituitary then signals the adrenal glands. In response, the outer part of the adrenal glands releases cortisol. Cortisol is often described as the stress hormone, but that phrase can be misleading if it makes cortisol sound like a villain. Cortisol helps regulate energy availability, blood sugar, immune activity, inflammation, blood pressure, and daily rhythms. It naturally rises and falls across the day, usually reaching higher levels in the morning as the body prepares for waking activity. During stress, cortisol helps sustain the body's response over a longer period than adrenaline. It is not bad by itself. The problem is not cortisol existing. The problem is when stress systems are repeatedly activated or remain elevated without enough recovery. Hans Selye was one of the major figures in early stress research. In the 20th century, he described what he called the general adaptation syndrome, a pattern of alarm, resistance, and exhaustion that he observed in animals exposed to ongoing physical stressors. His work helped establish stress as a serious biological concept, not just a vague feeling of strain. Modern stress science is broader and more nuanced than Seeley's original model, but his research helped bring attention to the idea that the body responds to demands in patterned, measurable ways. A more modern concept is allostasis. Homeostasis means maintaining internal stability, such as keeping temperature, blood pressure, and blood chemistry within workable ranges. Allostasis means maintaining stability through change. The body does not preserve balance by staying still. It preserves balance by adjusting. Heart rate changes, hormones shift, blood vessels tighten or relax, breathing changes, attention changes. The nervous system and endocrine system constantly alter the body's state to match what seems necessary. Bruce McEwen was an important researcher in the study of allostasis and allostatic load. Allostatic load refers to the long-term cost of repeated or prolonged physiological strain. In other words, the stress response may be helpful in short bursts, but costly when it is activated too often, too intensely, or for too long without repair. A fire alarm is useful when there is a fire. A fire alarm that goes off every few minutes because someone made toast, opened a window, or looked at it funny becomes less helpful. The nervous system's alarms are more complex than that, but the principle is similar. Stress changes the body in many connected ways. Heart rate can increase so blood moves more quickly. Blood vessels can narrow in some areas and widen in others, redirecting circulation. Breathing can become faster to support oxygen exchange. Muscles may tighten, preparing for movement but sometimes leaving the jaw, shoulders, neck, or back feeling stiff. Attention can narrow toward possible threat or urgent tasks. Digestion may slow because the body is temporarily prioritizing readiness over long, comfortable processing. Sleep pressure can be affected because the nervous system may keep the brain more alert when it thinks vigilance is needed. Stress also interacts with immune signaling. Short-term stress can temporarily mobilize aspects of immune defense, preparing the body for possible injury or infection. Longer-lasting stress can alter immune balance and inflammation in more complicated ways. It can affect how the body responds to illness, how fatigue is felt, and how inflammation communicates with the brain. Stress can also change pain sensitivity. Sometimes pain is dampened during immediate danger, allowing action to continue. At other times, especially with prolonged stress or poor recovery, pain pathways may become more sensitive, making the body feel more guarded and reactive. This is one reason safety matters so much to the nervous system. Safety is not only an idea, it is a body state. When the nervous system judges the environment as safe enough, the body can allow more energy for digestion, repair, sleep, social connection, and quiet attention. When the world feels uncertain, demanding, or threatening, the body may shift toward readiness. That shift can happen before conscious thought has clearly explained the situation. A sound, a memory, a facial expression, a deadline, or a bodily sensation can all influence the nervous system's alarm settings. The stress response becomes harmful not because it exists, but because biology needs rhythm. Activation and recovery belong together. Effort and rest belong together. A temporary rise in heart rate, alertness, cortisol, and muscle readiness can be useful. But if the body is repeatedly pushed into activation without enough time to settle, the same systems can become costly. Sleep may become lighter, digestion may become unsettled, muscles may remain tense, attention may become jumpy, pain may become louder, the immune system may receive confusing signals, the body may begin to feel as if it is always bracing for something, even during moments that should be calm. This does not mean the nervous system is broken when it responds to stress. Usually it is trying to protect. It is trying to predict what is needed. It is trying to prepare the organism for the next demand. But protective systems can become overtrained. They can learn to expect danger too readily. They can keep the body on alert long after the original challenge has passed. In that sense, stress is not simply an outside pressure. It is also an internal interpretation, a set of bodily adjustments shaped by the nervous system's best guess about what the world is asking. Stress shows again how quietly the nervous system runs the body. It adjusts the heart, lungs, blood vessels, muscles, digestion, hormones, immunity, sleep, and attention according to whether life feels safe, difficult, uncertain, exciting, or threatening. Much of this happens beneath awareness. By the time a person notices a tight chest, restless stomach, clenched jaw, racing thoughts, or sudden alertness, the nervous system has already begun shifting the internal settings. The body is not a calm machine occasionally interrupted by stress. It is a living system always adjusting to conditions. Sometimes those adjustments are brief and useful. Sometimes they become heavy from being carried too long. Beneath the surface of thought, the nervous system is constantly asking what is needed now, what might happen next, and whether it is safe to soften. Stress is one of its answers, not always comfortable, not always accurate, but deeply rooted in the body's ancient effort to keep itself alive. Sleep can look like a disappearance from the outside. The body becomes still, the eyes close, the voice quiets, and the busy surface of waking life seems to soften into darkness. But sleep is not the nervous system switching off. It is an active and highly organized state shaped by changing patterns of brain activity, body regulation, memory processing, immune signaling, hormone release, temperature control, and restoration. The body may look peaceful, but beneath that peace, the nervous system is quietly rearranging the night. Sleep comes in different stages, and the two broad categories are non-rapid eye movement sleep and rapid eye movement sleep. Non-rapid eye movement sleep includes lighter sleep and deeper slow-wave sleep. During deeper non-rapid eye movement sleep, brain activity becomes more synchronized, heart rate and breathing often slow, blood pressure tends to fall, and the body becomes less responsive to the outside world. This is the kind of sleep that can feel heavy and deep, the sort where waking someone may produce a confused expression, and possibly the emotional tone of a startled potato. Rapid eye movement sleep is different. During rapid eye movement sleep, brain activity becomes more active and more varied, in some ways closer to waking patterns. The eyes move rapidly beneath closed lids. Dreaming is especially strongly associated with this stage, although dreams can also occur during non-rapid eye movement sleep. At the same time, most skeletal muscles become temporarily relaxed or inhibited, a state called muscle atonia. This helps prevent the body from acting out most dreams, which is considerate, given what the dreaming brain sometimes decides counts as a sensible storyline. The timing of sleep is strongly influenced by the circadian system. A key part of this system is the suprachiasmatic nucleus, a small region in the hypothalamus that acts as the brain's main circadian clock. It receives information about light from the eyes and helps coordinate daily rhythms across the body. Light in the morning helps signal daytime. Darkness helps support the release of melatonin from the pineal gland, which contributes to the body's preparation for sleep. Melatonin does not simply knock a person unconscious. It is more like a chemical signal of biological night, helping the body know when the world outside is dimmed enough for rest. The nervous system also contains circuits that help control the transition between waking and sleep. The ventrolateral preoptic area, located in the hypothalamus, promotes sleep by inhibiting arousal systems. Orexin neurons, also in the hypothalamus, help stabilize wakefulness and prevent the brain from slipping too easily between states. The ascending arousal system includes networks in the brainstem and forebrain that release chemical messengers such as acetylcholine, norepinephrine, serotonin, dopamine, and histamine. These systems help keep the brain awake, alert, and responsive. Falling asleep involves a carefully balanced shift, not a simple power cut. the discovery of rapid eye movement sleep is closely linked with Nathaniel Kleitman and Eugene Aserinsky. In the early 1950s, Aserinsky, working with Kleitman at the University of Chicago, observed periods of rapid eye movement in sleeping infants and adults. These periods were associated with vivid dreaming and distinctive brain activity. Their work helped transform sleep from something that seemed passive into something scientifically rich and dynamic. Sleep was no longer just the absence of waking. It was a structured biological state with its own rhythms and mysteries. Across the night, the nervous system cycles through sleep stages several times. Early in the night, deeper non-rapid eye movement sleep is often more prominent. Later in the night, rapid eye movement sleep periods tend to become longer. These cycles are not perfectly identical, and they can be shaped by age, stress, illness, light exposure, sleep deprivation, substances, and daily routine. The sleeping brain is organized, but not mechanical in the dull sense. It has rhythms, variations, and a slightly mysterious confidence in its own timetable. Body regulation changes as sleep deepens and shifts. Breathing usually becomes slower and more regular during non-rapid eye movement sleep, while it can become more variable during rapid eye movement sleep. Heart rate and blood pressure often decrease during deeper, non-rapid eye movement sleep, then become more variable during rapid eye movement sleep. Temperature regulation also changes. The body tends to cool as sleep begins, and the brain adjusts blood vessel tone, sweating, shivering, and heat loss across the night. Muscle tone decreases during sleep, especially during rapid eye movement sleep when most voluntary muscles are strongly inhibited. The autonomic nervous system changes its balance as well. During restful non-rapid eye movement sleep, parasympathetic activity often becomes more dominant, supporting slower heart rate and recovery. During rapid eye movement sleep, autonomic activity can become more irregular, with changes in breathing, heart rhythm, and blood pressure. The sleeping body is not simply calm in one unchanging way. It moves through different forms of regulation, each with its own pattern. Dreams are brain-generated experiences during sleep. They can be vivid, emotional, fragmented, ordinary, strange, or so confidently nonsensical that waking up feels like escaping a committee meeting run by clouds. Rapid movement sleep is especially associated with vivid dreaming, but dreaming can also occur during non-rapid eye movement sleep, often with a different quality. Scientists still study why dreams happen, and there is no single complete explanation. They may involve memory processing, emotional regulation, prediction, imagination, and the brain's tendency to build experience even when mostly disconnected from the outside world. Sleep shows that consciousness is not the only sign of nervous system activity. When awareness fades, the nervous system keeps breathing moving, adjusts the heart, shifts temperature, changes muscle tone, processes memory, regulates hormones, manages arousal, and protects the body through the night. The sleeper does not need to supervise any of this. Rest depends on not needing to. So even in the quietest hours, the nervous system has not abandoned its post. It has simply changed its mode of work. Beneath closed eyes and softened muscles, it continues to run the body with remarkable precision, letting consciousness drift while the deeper systems keep watch. The nervous system is not fixed like a finished building. It is alive, changing, and constantly revising itself. Every movement practiced, every sensation repeated, every memory formed, every injury adapted to, and every skill slowly learned can alter the way nervous tissue is organized. This ability is called neuroplasticity. It means that the nervous system can change its connection, strength, structure, and function in response to development, learning, injury, practice, and experience. Neuroplasticity does not mean the brain can magically become anything at any time. Biology has limits, and some changes are easier in childhood than in adulthood. But the nervous system remains more flexible than people once imagined. Connections between neurons can become stronger or weaker. Some networks can become more efficient with use. sensory maps can shift, motor skills can become smoother, habits can become easier to trigger. After injury, surviving circuits may sometimes adapt, compensate, or reorganize. The nervous system is not a stone carving. It is more like a landscape of paths, where repeated journeys make some routes clearer, faster, and more inviting. One of the most famous ideas in this field is associated with the Canadian psychologist Donald Hebb. Hebbian learning is often summarized with the phrase cells that fire together wire together. The principle is that when neurons are repeatedly active at the same time, the connection between them can become stronger. This is a useful shorthand, but the real biology is more detailed. Neurons do not simply shake hands once and become best friends forever. Timing, receptor activity, chemical signals, gene expression, inhibition, attention, sleep, and wider network state all matter. Still, Hebb's idea captured something essential. Learning changes the relationships between cells. At the synapse, this change can happen through synaptic plasticity. Synaptic plasticity refers to changes in the strength of communication between neurons. If one neuron repeatedly helps activate another, the synapse between them may become more effective. This strengthening is known as long-term potentiation. In other cases, synaptic communication may weaken, a process called long-term depression. Both are important. Learning is not only about making signals stronger, it is also about refining, quieting, and removing what is less useful. A nervous system that only strengthened everything would be like a person keeping every single note, receipt, instruction manual, and mysterious spare cable forever. Eventually, organization would suffer. Long-term potentiation has been studied especially in the hippocampus, a brain region deeply involved in forming many kinds of new declarative memory. Declarative memory includes memories that can be consciously recalled, such as facts and events. The hippocampus does not store every memory like a tiny filing cabinet hidden in the brain. Memory is distributed across networks, but the hippocampus is crucial for binding aspects of experience together, including place, time, context, and meaning. It helps turn moments into memories that can later be recalled. A careful historical example comes from Henry Molaison, often known in scientific literature by his initials, although the full name is clearer for voiceover. In the 1950s, Molaison had surgery to treat severe epilepsy. The operation removed parts of the medial temporal lobes, including much of the hippocampal region on both sides. Afterward, he could still hold information briefly and remember much of his earlier life, but he was profoundly impaired in forming many new long-term declarative memories. His case became one of the most important in neuroscience, because it showed that the hippocampus and related medial temporal lobe structures are essential for forming new memories of certain kinds. Memory research also gained important insight from simpler nervous systems. Eric Kandel studied learning and memory in the sea slug Aplysia, an animal with large, accessible neurons. This might sound like an unlikely place to look for the biology of memory, but simple systems can reveal general principles more clearly. Kandel's work showed how changes in synaptic strength could support forms of learning. The sea slug did not need to write poetry or remember where it left its keys to be scientifically useful. Its nervous system helped reveal how experience can alter communication between cells. Plasticity also shapes movement. When a person practices a skill, the nervous system becomes better at coordinating the required patterns. Motor learning involves the motor cortex, cerebellum, basal ganglia, spinal circuits, sensory feedback, and muscles. At first, a new movement may feel clumsy and overly conscious. With repetition, it can become smoother, faster, and less mentally demanding. The nervous system learns the timing, force, sequence, and expected feedback. Practice does not only train the muscles, it trains the circuits that command, predict, and correct movement. Myelination also contributes to efficiency. Myelin, the fatty insulating layer around many axons, helps signals travel more quickly and reliably. Repeated use of certain pathways can influence myelination over time, especially during development and skill learning. This does not mean practice simply wraps every used pathway in magical insulation, but it does mean that nervous system efficiency can improve through structural change as well as synaptic change. The brain and body gradually become better tuned to repeated demands. Habits show another side of plasticity. A habit is not merely something a person chooses over and over. It is a learned pattern in nervous system circuits, especially involving the basal ganglia. With repetition, certain actions become easier to start and harder to interrupt. This can be helpful when the habit is useful, such as brushing teeth, typing, driving a familiar route, or making tea with minimal philosophical struggle. It can be less helpful when the habit is unwanted. The same plasticity that allows skill also allows unhelpful patterns to become deeply worn paths. Learning, memory, practice, and habit all show that the nervous system does not only run the body moment by moment, it gradually reshapes how the body senses, moves, reacts, expects, and remembers. Every repeated experience leaves some possibility of change. Some changes are tiny and temporary, others become durable features of the person's inner landscape. Beneath awareness, the nervous system is not just carrying signals, it is rewriting the routes those signals may take tomorrow. The nervous system is often pictured as something sealed away inside the skull, as though the brain were a private little kingdom floating above the messier affairs of the body. But the real nervous system is not isolated. It is deeply connected with the immune system, the endocrine system, the bloodstream, the gut, the muscles, the skin, the lungs, the heart, and the organs that quietly keep the body alive. The brain does not simply send commands downward, it also listens. It receives news from the body constantly, and that news can shape mood, attention, pain, appetite, temperature, sleepiness, energy, and the general feeling of being well or unwell. This conversation between the nervous system and the immune system is called neuroimmune communication. It is one of the clearest signs that the body is not divided into neat departments. Immune cells can release chemical messengers called cytokines. These cytokines help coordinate inflammation, defense, repair, and communication during infection or injury. The nervous system can detect many of these signals directly or indirectly, and when it does, it may change the body's state. A person may feel tired, cold, heavy, sensitive, low in appetite, less social, or more drawn towards sleep. These feelings are not random inconveniences. They are part of a coordinated biological response. Inflammation is not automatically bad. Inflammation is part of how the body responds to damage, infection, and threat. It helps recruit immune activity, isolate problems, and begin repair. But inflammation also has to be regulated carefully, because too little can leave the body vulnerable, while too much or too long can become harmful. The nervous system is involved in this regulation. It can influence immune activity through autonomic pathways, hormones, pain pathways, sleep changes, and behavior. The immune system can, in return, influence the nervous system through cytokines, inflammatory signals, temperature changes, and chemical messages carried in the bloodstream. Microglia are especially important in this story. They are immune like cells of the central nervous system, living within the brain and spinal cord. Microglia constantly survey their surroundings, respond to injury or infection, help remove debris, and play roles in development and synaptic pruning. They are not simply tiny emergency workers waiting for disaster. They are part of the brain's ongoing maintenance system. When microglia become activated by inflammation or injury, they can change the chemical environment around neurons. This can influence pain sensitivity, fatigue, mood, learning, and the way the brain responds to further signals. Pain pathways also sit at the meeting point between the nervous system and immune activity. During injury or inflammation, immune cells can release substances that make nociceptors more sensitive. This is one reason an inflamed area can feel tender, warm, swollen, and painful. The nervous system becomes more protective around tissue that may need guarding. That sensitivity can be useful when it prevents further damage, but if the alarm remains turned up too high, the body can become uncomfortable in a way that outlasts the original problem. Once again, the nervous system is trying to protect, though sometimes with the enthusiasm of a guard dog barking at a falling leaf. One familiar whole-body response is fever. Fever involves immune signals communicating with the brain, especially regions connected with temperature regulation. The body raises its temperature set point, often producing chills as it works toward a higher internal temperature. Fever can help create conditions that make it harder for some pathogens to thrive and can support immune responses, though very high or prolonged fever can become dangerous. More often, mild to moderate fever is part of the body's organized defense. It is not just heat. It is a nervous system and immune system negotiation about what temperature might help the body respond. The tiredness that comes with illness is also meaningful. Sickness behavior is the name given to a collection of changes that often appear during infection or inflammation. These can include tiredness, reduced appetite, social withdrawal, lower motivation, altered temperature, increased sleep pressure, and a general desire to do very little except lie down and become one with the blanket. This is not laziness. It is an adaptive body state. Rest reduces unnecessary energy use. Reduced appetite may temporarily shift resources. Social withdrawal can limit spreading infection. Increased sleep supports immune regulation and recovery. The body pulls the organism inward so resources can be directed toward defense and repair. The vagus nerve is one of the major communication routes between the internal organs and the brain. It carries signals from organs including the heart, lungs, digestive tract, and other internal tissues toward the brainstem, and it carries parasympathetic signals from the brainstem back toward the organs. In relation to interoception, the vagus nerve helps the nervous system sense the internal condition of the body. In relation to inflammatory signaling, it is involved in pathways that help the brain monitor immune activity and influence aspects of the inflammatory response. The vagus nerve is not a magic calm button, but it is a major two-way information route between the brain and the living interior. The brain also has its own specialized fluid environment. One area of ongoing research is the glymphatic system, a proposed waste clearance pathway associated with movement of cerebrospinal fluid through and around brain tissue. This system is thought to help clear certain metabolic waste products from the brain, and it appears to be strongly linked with sleep. The neuroscientist Maken Nedergaard has been closely associated with research on the glymphatic system, helping bring attention to how the sleeping brain may support cleaning and fluid movement. The science is still developing, and researchers continue to study exactly how this system works in humans. But the broader idea is powerful. The sleeping brain is not idle. It may be performing quiet maintenance that waking life depends on. The gut-brain axis is another major example of body-wide communication. It includes nerves, hormones, immune signals, microbial metabolites, blood chemistry, and the enteric nervous system. The enteric nervous system is the network of neurons embedded in the digestive tract, helping coordinate movement, secretion, and local digestive reflexes. The gut also contains many immune cells, and the microbes living there produce metabolites that can influence the body's chemistry. These signals can affect digestion, appetite, inflammation, and sometimes brain function. But this should be kept in perspective. Gut microbes do not secretly control a person's personality like tiny bacterial puppeteers with a clipboard. The gut-brain axis is real, but it is complex, indirect, and part of a larger system. Muscles also talk back. During movement, muscles release chemical signals called myokines, and they send sensory information about stretch, tension, fatigue, and position. Exercise can influence brain blood flow, inflammation, mood, sleep, metabolism, and nervous system plasticity. The bloodstream carries hormones, nutrients, oxygen, carbon dioxide, immune signals, and waste products. The endocrine system releases hormones that shape stress, growth, appetite, reproduction, sleep timing, and energy use. Organs send messages about fullness, pressure, chemical balance, and discomfort. The body is not silent below the neck. It is constantly reporting its condition. This is why the nervous system cannot be understood as a brain giving orders to a passive body. It runs the body partly by listening to the body. It interprets signals from organs, blood, immune cells, muscles, the gut, and the skin. It asks whether the body has enough energy, whether tissues are threatened, whether rest is needed, whether the environment is safe, whether inflammation is rising, whether digestion is active, and whether pain should be amplified or softened. Consciousness may notice only a mood, a heaviness, a chill, a restless stomach, or a wave of sleepiness. But underneath that feeling is communication across many biological systems. The body is therefore not a machine controlled from one central switchboard. It is a living conversation. The nervous system helps coordinate that conversation, but it also depends on it. It listens, adjusts, predicts, protects, and responds. It turns immune activity into fatigue, organ signals into bodily feeling, inflammation into caution, gut signals into appetite or discomfort, and sleep into repair. Quietly, beneath awareness, the body talks back, and the nervous system answers. The ordinary feeling of being alive can seem smooth and simple from the inside. There is a body, a world, a stream of thoughts, a sense of balance, a rhythm of breathing, a mood in the background, and a quiet awareness of where the hands, feet, face, and heartbeat belong. It feels like one continuous experience. But beneath that smooth surface, the nervous system is combining many processes at once. Sensation, movement, autonomic regulation, memory, emotion, attention, pain, balance, and internal body monitoring are all being woven together into the strange and familiar feeling of being here. A touch on the skin is not only touch, it arrives with context. A sound is not only vibration. It may become warning, comfort, music, language, or background noise. A change in heartbeat is not only a rhythm in the chest, it may influence anxiety, excitement, calm, or effort. The body is not simply sending information up to the brain like reports arriving at an office. The nervous system is constantly interpreting what those signals mean, comparing them with memory, expectation, and current need. Attention plays a major role in this process. Conscious awareness can only hold a tiny fraction of what the nervous system is processing. At any moment, the body is detecting pressure under the feet, the temperature of the skin, the position of the joints, the movement of the eyes, the rhythm of breathing, signals from the gut, the soundscape around the head, the shape of words, the emotional tone of a memory, and countless small changes in posture. If all of it arrived in awareness equally, ordinary life would become impossible. Consciousness would be buried under a landslide of details, including several that are best left politely ignored, such as the exact position of the tongue, or the way one sock suddenly feels more present than the other. Attention is therefore a selection process. The nervous system filters information, raises what seems important, lowers what seems irrelevant, and updates those priorities as the situation changes. A distant noise may vanish into the background until it sounds like footsteps. A faint ache may become louder when the body is tired. A familiar room may feel calm until something looks slightly out of place. Attention is not just a spotlight controlled by will. It is shaped by threat, interest, memory, emotion, bodily need, and the nervous system's constant search for what matters now. A useful modern framework for understanding this is called predictive processing. In broad terms, predictive processing describes the brain as an organ that does not passively wait for the world to arrive. Instead, it constantly uses prior information and incoming sensory signals to update its best model of the body and the world. The brain predicts what is likely to happen. compares those predictions with what the senses report, and then adjusts. This does not mean the brain invents reality from nothing. It means perception is an active process, built from a meeting between expectation and evidence. This helps explain why the world usually feels stable. The eyes move constantly, yet the room does not seem to jump around. The body shifts and sways, yet standing can feel still. The heart beats, digestion moves, muscles stretch, and clothes press on the skin, yet most of these signals remain in the background. The nervous system is always predicting, correcting, filtering, and smoothing. It turns a storm of signals into a usable world. Conscious control is real, but it is partial. A person can choose to stand, speak, reach, breathe deeply, look toward a sound, or shift attention. Deliberate control matters. It allows planning, restraint, learning, communication, and creativity. But many processes that make deliberate control possible happen before or beneath awareness. Posture is adjusted before a fall. Breathing continues during sleep. Emotions change the body before their causes are fully understood. Sensations are filtered before they become conscious. Blood pressure, pupil size, digestion, muscle tone, and pain sensitivity are altered without needing a formal request from thought. The nervous system does not run the body like a commander shouting orders from the brain. That image is too simple. It is more like a layered network of loops, predictions, reflexes, feedback signals, chemical adjustments, and local circuits. The brain influences the spinal cord, but the spinal cord also processes and responds. The gut sends signals to the brain, but the brain also changes gut activity. The immune system changes nervous system behavior, and the nervous system helps regulate immune responses. Muscles report their state, and motor circuits adjust movement in return. The body is not ruled from one throne. It is coordinated through conversation. This is why effortless living is partly an illusion, not because life is fake, but because ease hides labour. Walking across a room feels simple because the nervous system manages balance, vision, proprioception, muscle timing, reflexes, attention, and prediction together. Resting in bed feels still because breathing, heart rate, temperature, digestion, and sensory filtering continue without becoming a task. Even thinking quietly depends on the body being held in a workable state by systems that rarely announce themselves. The nervous system quietly runs the body through countless small acts of regulation. It notices pressure, adjusts posture, raises or lowers pain, shifts heart rhythm, prepares muscles, interprets internal signals, filters sound, changes tension, supports memory, and steadies the world. Most of this becomes noticeable only when it changes, fails, or demands attention. A dizzy spell reveals balance. A racing heart reveals autonomic regulation. Pain reveals protection. Fatigue reveals energy management. Breathlessness reveals a rhythm that was being handled silently a moment before. Stillness, then, is not inactivity. Even now, in rest, the nervous system is working carefully beneath the surface. It is keeping the body balanced enough, responsive enough, and alive enough for awareness to soften. The quiet body is not empty of effort. It is full of hidden coordination, steady signals, and delicate adjustments, all carrying on in the background so that life can feel, for a little while, beautifully effortless. How your nervous system quietly runs your body is, in the end, a story about hidden coordination. It is the story of a living network that senses the outside world, monitors the inside world, coordinates movement, adjusts organs, protects tissues, shapes emotion, supports sleep, and filters awareness. It does not do this as a single dramatic switch, or as a lone command center issuing orders from the brain. It does it through countless small acts of regulation, most of them happening beneath the surface of thought. The nervous system begins with cells. Neurons carry signals, but they are not simple wires. They receive, process, and pass information through branching dendrites, cell bodies, axons, synapses, and chemical messengers. Glial cells support them, protect them, insulate them, nourish them, and help shape the environment in which signaling can happen. Astrocytes, oligodendrocytes, Schwann cells, microglia, and ependymal cells all remind us that the nervous system is not built from one heroic cell type doing everything alone. Biology, as usual, prefers teamwork. With a slight tendency toward overcomplication, its signals are electrical, but not in the way a plug socket is electrical. Nerve cells use charged ions moving across membranes. Sodium ions, potassium ions, chloride ions, selective channels, and the sodium-potassium pump help create the conditions for action potentials, those fast-travelling waves of depolarization and repolarization that allow information to move through living tissue. Then, at synapses, electricity often becomes chemistry. Neurotransmitters such as glutamate, gamma-aminobutyric acid, acetylcholine, dopamine, serotonin, norepinephrine, histamine, glycine, and endorphins help one cell influence another. Some signals are strengthened, some softened, some blocked, some repeated, and some quietly ignored. The spinal cord carries information between the brain and the body, but it also processes signals locally. It organizes reflexes, supports posture, and helps coordinate movement. Reflex arcs allow the body to pull away from heat, blink, cough, and adjust balance before conscious awareness has fully caught up. Charles Sherrington's work helped reveal that these reflexes are not crude twitches, but coordinated patterns within a larger nervous system. The body can act before thought arrives, and very often that is exactly what keeps it safe. Deeper still, the brainstem keeps essential rhythms moving. The midbrain, pons, and medulla oblongata help support alertness, eye movements, swallowing, breathing, heart rate, blood pressure, and protective reflexes. The prebuciner complex helps generate respiratory rhythm. Baroreceptors in the carotid sinus and aortic arch send feedback about blood pressure. The vagus nerve carries messages between the brainstem and organs, including the heart, lungs, and digestive tract. These are not glamorous functions, perhaps, but they are the difference between life as an ongoing process and life as a very short experiment. The autonomic nervous system adjusts the body's background settings. The sympathetic nervous system helps prepare the body for readiness, alertness, effort, and energy mobilization. The parasympathetic nervous system supports rest, digestion, recovery, and conservation. The enteric nervous system helps coordinate the digestive tract, not as a thinking brain in the gut, but as a semi-independent network built for local control. Through these systems, the nervous system changes heart rate, blood vessel diameter, sweating, digestion, pupil size, bladder control, and glandular activity, often before conscious thought knows anything has shifted. Sensation gives the body its map of the world. Touch, pressure, vibration, temperature, pain, body position, and movement all arrive through specialized receptors and pathways. Mechanoreceptors in the skin detect different forms of contact. Proprioception tells the nervous system where the limbs are. The vestibular system helps balance the body through the semicircular canals, utricle, saccule, and vestibular nerve. Vision begins in the retina. Hearing begins with vibration in the cochlea, and both become nervous system processes long before they become ordinary experience. The body feels placed in the world because the nervous system is constantly building that placement from many signals at once. Pain shows the protective side of this system. Nociceptors detect potentially harmful stimuli, but pain itself is generated by the nervous system as a warning experience. Patrick Wall and Ronald Melzack's gate control theory helped show that pain is modulated, not simply relayed. The spinal cord, brainstem, thalamus, somatosensory cortex, insula, anterior cingulate cortex, and prefrontal cortex can all contribute. Pain is real, but it is not a simple measurement of damage. It is protection, sometimes wise, sometimes overcautious, sometimes far too loud. Movement shows the nervous system's quiet choreography. The primary motor cortex, premotor cortex, supplementary motor area, basal ganglia, cerebellum, brainstem pathways, spinal motor neurons, and skeletal muscles cooperate to turn intention into action. A reach, a step, a swallow, or a blink depends on timing, prediction, correction, sensory feedback, and acetylcholine at the neuromuscular junction. The cerebellum refines movement. The basal ganglia help select and initiate it. The body moves smoothly because so much work is hidden. Emotion, stress, sleep, memory, and immune communication deepen the picture even further. The amygdala, hippocampus, hypothalamus, insula, anterior cingulate cortex, prefrontal cortex, and nucleus accumbens help link bodily state with feeling, memory, reward, threat, and meaning. Stress changes the heart, breath, muscles, digestion, attention, hormones, immunity, sleep, and pain sensitivity. Sleep is not shut down, but an active state shaped by non-rapid eye movement sleep, rapid eye movement sleep, the suprachiasmatic nucleus, the ventrolateral preoptic area, orexin neurons, and the ascending arousal system. Learning and memory reveal neuroplasticity, the nervous system's ability to rewrite its connections through experience, practice, and time. The nervous system is not only the seat of thought, it is a whole body regulator. It keeps life stable through feedback, prediction, correction, filtering, and constant adjustment. Many things feel effortless, not because they are simple, but because the nervous system performs them beneath conscious attention. Stillness is not silence. Rest is not emptiness. Even now, in quiet, the body is full of signals, rhythms, protections, and tiny acts of care. Beneath awareness, the nervous system is maintaining the fragile living balance that makes rest possible.